Hi everyone, this is Professor Eric Lobel. I'll be talking about the controlling the quantity of radiation PowerPoint today in lieu of giving this lecture because of the storms. So some of you have had the majority of this information in the lab, and unfortunately we have some math to do which is going to be a little bit challenging to do over a video format as it currently is set up. But let's give it a try. So we'll be talking about MA and time, we'll be talking about the mass reciprocity law, and we'll do some calculations both with figuring out the intensity of radiation when you change your distance, as well as maintaining your mass, which is what we did in the lab when you change your distance. So first of all, MA controls the amount of radiation produced by the X-ray tube each second. So this is known as our rate of exposure. Then we have the time that controls the length or the duration of the exposure. As we all know that both of these factors are quantity factors. They talk about how much radiation, how many electrons you're creating at the cathode, and how many photons you will be ultimately producing at the anode. We should be familiar with the calculation in order to create exposure, and that's MA times time. So if we multiply MA times time, we'll have a factor which controls the amount of radiation produced by the tube for one single exposure. As long as we come up with the same mass, whatever combination of factors that we use for MA and time will create the same blackening or density on the image. So for example, 100 MA times 0.5 or 400 MA times 0.125 or even 1000 MA times 0.05, as long as they all excuse me, as long as they all equal the same mass, in this case 50, you should get an image of all three exposures, if you were to do them in the lab, to where the density would look the same on all three images. They would have the same blackness. Here's the same example, just using milliseconds. In either case, this slide or the last, if your ultimate result is 5 mass, or the same mass for all three exposures, varying your MA and varying your time, you will get the same density. So no matter what combination of factors you used to achieve, in this case the elbow, where we changed different examples, you should get the same mass. Keep in mind, though, that this will only work if all other factors were the same. So KV was not varied, SID, focal spot, cassettes, you name it, same part. The only thing that changes here is your MA and your time. Now, there is a way to figure out how to do this so that you can get the same type of darkness. So in the previous slide we noted that the MA is increased, time must be decreased. In other words, if one goes up, the other has to go down. MA goes down, time has to increase. If time goes down, MA has to increase. In other words, it's kind of like a seesaw, and you're ultimately ending up in the same place. We say that the MA and the time needed to maintain density have a reciprocal relationship, and this is what I'm talking about. If you do the math here and you cross multiply, you would have the original MA times the original time, which is MAS, thus the original MAS is equal to the new MA times time, in other words, the new mass. So our goal in many cases is to keep the mass the same in order to maintain radiographic density. One way that this can be used is if we are worried about motion. If we have a particular technique where we know that the density will work out correctly, but the patient is moving and we need to decrease our time to try to restrain some of that motion, we would have an accordingly increase in our MA. Decrease the time, increase the MA. Same mass, same density. Now, when we're working with mass, as we talked about in the lab, you should be able to figure out any of the three variables, MA, time, or mass, provided that we have the other two. The calculations are fairly simple. If you want to find the mass, we're used to this one. It's MA times time. But let's say you wanted to find the time. It's MAS divided by MA. And let's say you wanted to find the MA. It's MAS divided by time. Here's the trick that I had shown many of you in the lab. If you cover up the unknown factor that you're interested in, you just need to perform the example. So if I cover up mass here, I'm left with MA times time. MA times time. If I were to cover up the time, because that's the one that I'm looking for, so you only cover up the variable that you are interested in solving, this would be MAS divided by MA. And similar to that, if we covered up MA, this would be mass divided by time. So you cover up the unknown factor, or the factor that you're interested in, and then perform the operation. Now, radiation intensity versus distance. The intensity of radiation refers to the amount of radiation measured at a particular distance from the source. When we talk about intensity, remember this is a quantity term. We are counting photons. So as you already know, the amount of radiation reaching the film decreases as the SID is increased. So if you pull the tube away and you create a longer SID, in other words, you're going from, let's say, 40 inches to 72 inches, you're further away, photons have a longer distance to travel, so more of them are going to die in the air. So that intensity, the number of photons, will go down. So this is a inversely related to SID ramification. In other words, the intensity is inversely related to SID. As you increase SID, you're going to decrease the intensity. This actual relationship is known as the inverse square law that we've discussed. The inverse square law specifically says that if you double the distance, you'll end up with a quarter the intensity of the X-ray beam. If you cut the distance in half, meaning you're closer, going from 40 inches to 20 inches, or let's say 72 inches to 36 inches, you're going to have 4 times the intensity. In other words, 4 times more photons, 4 times more exposure. The way the inverse square reads is I2 over I1 is equal to SID, or your distance 1, over your distance 2 squared. It doesn't matter whether you put the 1 on top or the 2 on top, as long as the sides don't match. In other words, intensity 2 goes with distance 1, and intensity 1 goes with distance 2. Right? This right here cannot match this one here. So for some of this PowerPoint, you'll notice that I didn't write this out in this kind of format here. Instead, it looks a little bit like this. I2 divided by I1, which is the same as this part, is equal to SID1 divided by SID2, the second distance, squared. So here's an example. Okay, this is not quite how I would do it on the board, but math is the same whichever way you do it, as long as you come up with the correct answer. Here we're asking a question. If you had an exposure that was done at 40 SID, okay, so 40 SID, that's your first distance, and it delivers 100 milliroentgen. Okay, this is the actual dose, milliroentgen. Here's our intensity 1, 100 milliroentgen. to the film. How much radiation will reach the film if the same exposure is made from a 60-inch SID? Okay, that's our second SID here. And we want to know how much the new intensity would be. This is our unknown, our second intensity. So what you have up here in these first 4 lines are really just the variables you're working with. Now we just have to plug them in. So we don't know our new intensity, I2, over our first intensity, 100 milliroentgen, is equal to SID1, which is the 40. Notice that the 1 is opposite the 2, so that's correct, over our new SID of 60 inches squared. Now, you see this 40-60. If those were flip-flopped, you're going to end up with the wrong answer. So the first thing that you should do before you really even attempt this problem is to decide at the end of this problem, what kind of number should I have? If I am going from an exposure at 40 inches and I am now going to an exposure at 60 inches, I'm moving the SID further out. So I should be getting a lower amount of radiation. And you'll see that we will be getting a lower amount of radiation, 44 versus 100. But in any case, let's go through the rest of the problem. I2 is our unknown, divided by intensity 1, 100 milliroentgens, is equal to our first distance, 40, divided by our second distance, 60. So if we reduce this, we get 2/3 squared. And when we do the math, 2 times 2, 4, 3 times 3, 9. When we continue down, we have intensity 2 is equal to 4/9 times 100, which gives us our intensity of 44 milliroentgens. Now, that was the inverse square law. Right here we have a formula that's designed to maintain our density. This is what we went over in the lab and had a laboratory about. So this is a formula that allows us to maintain density when we have a change in SID. Sometimes it's referred to as the maintenance of density formula. And it states, if the radiation intensity decreases with increasing SID, which is very true, right? When the SID increases, right, we're going to have a smaller intensity. The radiographic density will decrease also. In order to maintain the same density when changing the SID, we must change the mass in direct proportion. So remember, this is a direct proportion. 2 matches with 2, 1 matches with 1. Remember that in the last problem, it was inversely proportional, and we were dealing with intensity and distance. Now we are dealing with mass and distance, so the variables are also different. Although the two formulas do happen to appear very similar, please keep in mind that they are not. So, in order to maintain the same density when changing the SID, we must change the mass in direct proportion to the square of the SID. So we have mass 2 over mass 1, our first mass, is equal to our second distance over our first distance. Now remember, if you write this down, you can certainly change this and make this the first mass and this the second. But then, of course, you have to make sure that this is also maintained. So always have to have 2 goes with 2, 1 goes with 1. If you want to switch these denominators with the numerator, that's fine as long as it stays a direct proportion. Again, for our math in this PowerPoint, it's going to be written a little bit differently. Mass 2 over mass 1 is equal to distance 2 over distance 1. So 2 goes with 2, 1 goes with 1, and of course this side is squared. Let's try a sample problem. If an exposure of 10 mass, that's our first mass, at 40 inches SID, that's our first SID right here, produces the correct density on a radiograph of the knee. What would be the new mass, or what mass will be needed to produce the same density if we now go to 60 inches? So we don't know what our new mass is. That's what we're going to try to find out. But we do know that we have increased the SID. So if you're going to increase the SID, our intensity is going to go down because now we're further away from the image receptor. So we should know at this point that we're going to have to use more mass than 10. And as you'll see later on, we are going to get a higher number. When you're taking an exam, this is really the first thing you should think of before you even do the calculation and plug in everything. You should at least be able to probably eliminate an answer or two just because the number is going in the wrong direction. Let's try this example. So, our second mass is unknown. We're going to divide that by our first mass. So MAS2 over MAS1 is equal to the second distance divided by the first distance squared. So again, that's the hard part. Once you plug in all the numbers, the math is not too bad. It's MAS2 divided by 10 is equal to 3 over 2 squared, and all we did was said that 20 goes into 60 3 times, 20 goes into 40 2 times, so we reduced this fraction to make the math a little bit easier. You'll be given a calculator, so you don't even have to do this if you don't want to. Mass 2 over 10 is equal to 9/4, so we squared the above. 3 times 3 is 9, 4 times 4, 2 times 2 is 4. We're left with 9/4. Mass 2 is equal to 9/4 times 10. We kind of moved this over. And when you do this multiplication, you have 22.5 mass is your answer. So we would change our mass to 22.5 on this second exposure, provided that we now change the distance and everything else was the same. If we were to take a look at these two images, you should not be able to tell them apart, aside perhaps from slight change in magnification. The density, however, should remain the same. Okay, this particular slide I am not going to go over. It is a second way to maintain the density. It's a rule that also works. I prefer the other rules, so you can look at this on your own and try this if you like. Just want to show you something if I could here. Did find a rather nice website over here. It's www.convert, C-O-N-V-E-R-T, hyphen or dash me.com/en/convert/radiation. And this is a radiation calculator that's really nice. In terms of intensity, we've been dealing with milliroentgen down here. And in the lab, for some of you, we broke out the dosimeter, which was reading out the absorbed radiation dose in microgray over here. The way this works, though, is somewhat interesting. If I put in a number, everything changes. So if I put down that this person received 1 Roentgen and then hit convert, you'll see that all the numbers change here. Let me magnify this just a little bit. Okay, so if you take a look here, 1 Roentgen is equal to 1,000 milliroentgen, which is equal to 100,000 micro-Roentgen. That same 1 Roentgen in micro-gray is equal to 8,696. Excuse me. Although we measure a lot of what we do in dose equivalent, which is in millisieverts or millirem. So if we take a look at an example I have here, where we have a lumbar spine, X-ray is 900 millirem. Let's try that. 900 millirem. We'll go back here. Let me just reload this. Millirem 900. Okay, that's 9,000 microsievert, 9 millisievert, 9,000 microgray, and approximately 1 Rankine. So it's a nice little calculator. Well, that concludes today's lecture. I hope everyone managed to stay safe in the storm, and I will be communicating with all of you via email, and I am going to keep our quiz number 3, on the same date. So that will cover the lecture that we just talked about, as well as the processing lecture that we had prior to the midterm. Basically, just to cover myself, we are going to make sure that our quiz covers everything from the last quiz. If you have any questions, please feel free to email me. As many of you know, I will not be in school this week. I will be away at a conference, but I will try to look at my email. Thank you, everyone.